Hello and welcome. So today we are going to be looking at formation of ODE, formation of ordinary differential equations. ODEs can be formed when arbitrarily constants are eliminated from equations. So this is y is equal to x plus a all over x. Now once again I'm considering a function where y is a function of x. Y is a function of x. So what does that mean? It means that a is an arbitrarily constant. How do I know a is an arbitrarily constant? I know a is an arbitrarily constant because a is neither the dependent nor is it the independent variable. So it must be a constant. Likewise, you can say y is equal to ax squared plus bx. It means that both a and b are arbitrarily constant in this equation. Y is equal to cx plus c squared. So now in this equation, we only have one arbitrarily constant, which is c, and cx plus c squared. There's only one arbitrarily constant in this equation. Number 4, we have y is equal to a sine x plus b cos x. There are two arbitrarily constant in this equation. Y is equal to u e to the 3x plus v e to the x. There are two arbitrarily constant in this equation. Now, I want to bring something to your notice. The number of arbitrarily constant appearing in the equation will determine the order of the differential equation that will be formed when you eliminate those arbitrarily constant. So here, the differential equation that will be formed here will be of first order. So when you eliminate this a, you are going to get a first order differential equation. When you eliminate a and b, you get a second order. And when c is eliminated, now there's only one arbitrarily constant here. We only have one arbitrarily constant, which is c. You are going to also get a first order. If there are two arbitrarily constants, you are going to get a second order differential equation. And there are also two here, so you also get to an ODE of the second order. So let us take a look at this example and see how we can eliminate the arbitrarily constant to give us an ODE. So let us take a look at our first example. So y is equal to x plus a all over x. Now, how do we eliminate a to form the differential equation? We eliminate the a by differentiating. Now, you must be asking, how many times do we need to differentiate to form the differential equation? Well, corresponding to the number of arbitrarily constants that appear in the equation, that will determine how many times you need to take the derivative. So here, in this problem, we have only one arbitrarily constant, so we are only meant to differentiate once. Do not differentiate more than once. So let us get into the problem. So y is equals to x plus a all over x. Now we are going to take the derivative on both sides. That is differentiating both sides of this equation. We are going to have, if we differentiate y, you get 1. But y is a function of x. That is, y is a dependent variable in this equation. So you have to multiply by dy dx, which is the differential coefficient, times dy dx, which is equals to differentiating x, you get 1 plus. Now this is a all over x. If I take the derivative of a all over x, I can bring out the a out of the differential coefficient and say this is a times d dx of 1 all over x. Now 1 all over x can be written as x to the negative 1. All right. So I'm going to replace 1 over x by x to the negative 1. All right, so let us go to the next step. So this implies that the y dx is equals to 1. If I take d dx of x to the negative 1, I'm going to get, let's just put plus a there. Taking the derivative of x to negative 1, you have to multiply negative 1 by this. So it will be negative 1 times x. Now, you take away 1 from the power. So this is minus 1, which will give you minus 2. Right. Let us open the bracket. So dy dx is equals to 1 minus a. Now x to the negative 2 can be written as 1 all over x 2, 1 over x to the second power. So this will be 1 a all over x to the second power. Now we need to clear this fraction. So what do? We multiply each term by x squared. So this implies that x squared times dy dx is equals to, multiply x squared by 1, you only have x squared, minus, now a times a all over x squared times x squared, it will get rid of the x squared from the denominator, leaving you with a. Now we need to take this x squared to this side. We need to isolate a. We are looking for a, so that when we get the value of a, we can plug it back into this equation to find the ODE. All right, so let us take x squared to the other side. In doing so, this implies that x squared dy dx minus x squared, because x squared is crossing the equality sign, you have x squared is equals to minus a. Now let us get rid of this negative. What do? We multiply -1 to each term. If we do that, we have minus x squared dy dx, right, plus x squared is equals to a. So a is equal to this. Now the next step is to take this value and plug it back into this place. So let us do that. Let us do some cleaning first. Some cleaning. So let's take this equation. Y is equals to x plus. Now what is the value of a? We have the value of a to be this, so we are going to plug everything into this equation. I say that this is equals to x squared, this is minus x squared dy dx plus x squared divided by x. All right, so let us clean things up. Let's multiply x to each term. If we do that, we get xy is equals to, multiply x here, you get x squared, and you multiply x to this term, it will get rid of x. If you multiply x here and here, they cancel out, leaving you with if we open this bracket, you get this minus x squared dy dx plus x squared. Okay, let us take these terms to this side. If we do that, we have x squared dy dx, where minus x squared dy dx crosses the equality sign, becomes positive x squared dy dx minus x squared. We have another minus x squared here. All right, plus xy, and this will equal 0. Now we have two like terms here, we can add them together. So x squared dy dx minus 2x squared plus xy is equal to 0. All right, we can do a little bit of tidying. If we divide both sides by x squared, because I can say x appears here, it appears here, and it also appears here. So let us divide both sides by x squared. Dividing each term by x squared, if we divide this term by x squared, if you divide this term by x squared, you're going to get dy dx. If we divide this term by x squared, you only get -2. If you divide this term by x squared, you're going to get y all over x plus positive y all over x, and this is equal to 0. So just like as I had predicted, this equation is of first order because the differential coefficient is of the first derivative. So this is a first order differential equation, and it is gotten from this equation by eliminating the arbitrarily constant. And because the arbitrarily constant appears only once, it is only one arbitrarily constant in this equation, you only have a first order differential equation, and this is the differential equation formed from this equation. Now let us look at number 2. All right, so this is number 2 from the list of equations I gave to you earlier, and we have y is equal to ax squared plus bx. Now you can see there are two arbitrarily constant in this equation, so it means we are going to obtain an ODE of the second order. So let us solve it. Solution. So y is equals to ax squared plus bx. Now I would like to call this equation 1. Let me call this equation 1. Now, how many derivatives do we need to take here? We need to take 2 derivatives. We need to differentiate twice, because why? We have 2 arbitrarily constant in this equation, so we must differentiate twice. You cannot differentiate more than twice, and you cannot differentiate once. Okay, let us differentiate. If we differentiate y, what do you get? You get 1, but y is a function of x, so you have to multiply by dy dx. So this will be dy dx is equal to, if we differentiate ax squared, what do you get? This will be 2 times a. Take away 1 from the power, you're going to get, this is 2a. Taking away 1 from the power, you get x. Plus, if we differentiate bx, what do you get? You only get b. And let's call this equation 2. Let's differentiate again. So if we differentiate dy dx, you get d2y dx squared. So this will be d2y dx squared, which will be equal to, if we differentiate 2ax, what do you get? You get only 2a. If we differentiate b, you get what? You get 0. Because b is a constant, it is an arbitrarily constant. So let's call this equation 3. Alright, so we can just get rid of the 0 because it is 0, and just get rid of it. Now, we have to find the value of a, we have to find the value of b, right? So what do we do? From here, we can find the value of a by multiplying 1 over 2 to both sides of this equation. If we do that, you get 1 over 2 d2y dx squared is equals to a. Because 2 times 1 over 2 times 2 will give you 1. So multiply that will give you a. So now that we found the value of a, we have to put it in equation 2 to find the value of b. Let's do that. So from equation 2, we have that dy dx minus 2ax is equals to b. So I just made b the subject of the formula from equation 2 to obtain this. Now we have to replace a with this value. Let's call this equation 4, by the way. So we have to replace a by this value. So let us do that. So we get that dy dx minus 2, let's put the x together, x into this. This will be 1 all over 2 d2y dx squared is equal to b. All right, so let us clean this up. So we get that dy dx minus, now 2 times 2 will cancel themselves out, leaving you with minus x d2y dx squared, which is equals to b. Now we have found the value of b, we found the value of a. We have to take all of them and put it back into the original equation, that is equation 1. So let's call this equation 5, right? So we are going to put equation 4 and equation 5 into equation 1. All right, so let's do that quickly. All right, so this is the value, this is y. So we have to put a and b. We've gotten the value of b, and a was just equals to 1 over 2 d2y dx squared. That was the value of a. So we just have to put it back here and obtain the ODE. So y is equals to a, but a is this, so this will be, this is 1 over 2 d2y dx squared multiplied by x squared plus b. Now this is the value of b, dy dx minus x d2y dx goes to b. So we'll just use the value of b it is multiplying x. So let us put x outside and put the value of b into the bracket. So this is dy dx minus x, the 2y dx squared. All right, so let's clean this up. So y is equal to, this is a half, so this is a half. Okay, we have x squared here. Now always endeavor to put the x squared in front of the differential coefficient so that it doesn't look like you are taking a derivative. If you put it at the back, somebody can just look at it and assume maybe you are differentiating. If you're not differentiating, you are just taking the product of the two. Always endeavor to put it in front. So I'll just put it 1 over x squared, then followed by the 2y the x squared is squared plus this. So this is plus x the y the x times this will give you minus x squared the 2y the x squared. Okay, it looks like we have two like terms. We have the 2y, so this is minus x squared the 2y the x squared. Now this is the 2y the x squared. We have another differential coefficient of the 2y the x squared here. We can group them together, that is bringing them together. So y is equals to 1 over 2x squared the 2y the x squared. Bring this to this side, minus x squared the 2y the x squared, then plus x the y the x. All right, so this is a half, this is 1. We can take the differential coefficient out. So y is equals to, take this the 2y the x squared, since it appears in both ends, take it out. So you have the 2y the x squared into, this is a half x squared. So it's what you have here when you take this out is only half x squared. So put a half x squared. If you take the 2y the x squared out of here, you only have minus x squared plus what is left here, which is x the y the x. All right, so what do? Let's simplify this. This is a half x squared minus 1 x squared. What do we get? You get negative a half x squared, because this is a half negative 1. So what you get is y is equals to, I would like to bring it to the form. So this is 1 over 2 to be negative x squared the 2y the x squared, then plus this term plus x the y the x. All right, so I can take this to this side, but first of all, let me clear this fraction by multiplying each term by 2. If I multiply each term by 2, I get 2y is equal to, if you multiply this term by 2, the 2 cancel, so you have negative x squared the 2y the x squared plus 2x the y the x. Now I want to move everything to this side. So when this crosses the equality sign, you are going to have, I'll put it first. So this implies x squared the 2y the x squared minus 2x the y the x, and plus 2y, this will equal 0. This is the solution to this equation. That is, this is the ODE formed when you differentiate this equation twice, and you can see it is of the second order. So 2 arbitrarily constant will give you a second order differential equation. Okay, so this is the number 3 from the problems earlier, and this is y is equal to cx plus c squared. You can see that we only have one arbitrarily constant, which is c. So we are only going to obtain equation of what order? That's right, order 1. An ODE of the first order. So let us take a look at the solution. Now y is equal to cx plus c squared. Write it as y is equal to cx plus c squared. Now, how many derivatives do you need to take? You only need to take one, because we only have one arbitrarily constant. So let's differentiate y. If we differentiate y, get the y dx, which is equals to, if we differentiate cx, what do you get? You're only left with c. If you differentiate c squared, what do you get? You get 0. The derivative of a constant is 0, right? Okay. Now, what do we need to do? We don't need to do anything, because right now we found the value of c, and the only thing left is to substitute c back into this equation to obtain your ODE. So what do? We say y is equal to this is c, but c is just dy dx, cx. So we multiply this is dy dx, which is the value of c, times x, right? Plus c squared. Now we just square this dy dx because that is the value of c, plus dy dx or squared. Now let us rearrange this. So y is equal to, bring this x to the front, because if I'm not differentiating, if I'm just multiplying them, always put whatever is here in front of the differential coefficient. So this will be x dy dx plus dy dx or squared. Now if you like, you can leave it in this form. If you like, you can take everything to the other side. Let us do that, so that you have x, or sorry, you can just take y to the other side, so that you don't so that you avoid negative values. I don't know, I just like avoiding negative values. I do not know why. So this is x dy dx plus dy dx all squared. Now y is coming to this side, so this is minus y, and this is 0. So you can see the differential equation formed is of what? This is a first order differential equation, because the highest differential coefficient is 1, is of the first derivative. But that being said, the degree of this differential equation is of what? Degree 2, because the highest differential coefficient is raised to the power of 2. So it is of order 1, but degree 2. Okay, so this is problem 4, where we have y is equal to a sine x plus b cos x. Now I have to warn you, whenever you are dealing with sines and cosines, sometimes it gets trickier, because sine x and cosine x, no matter how you take their derivative, you can't get them to be 0. They can only change from sine to cosine or cosine to sine. So what you do is you try to use algebraic manipulation to obtain the value of a and b. Okay, let us look at it. So solution. So y is equal to a sine x, y is equal to a sine x plus b cos x. I'm going to call this equation 1. Okay, now how many derivatives do I need to take here? Of course, you need to take 2 derivatives, because we only have 2 arbitrarily constant, so you have to differentiate twice. So differentiating y, what do you get? You get dy dx. If you differentiate x sine x, what do you get? You're going to get a cos x. Differentiating b cos x, what do you get? You get negative b sine of x. Now let's call this equation 2. Let's differentiate this equation again, this very one. So differentiating again, what do you get? You get the 2y dx squared, which is equals to, differentiating a cos x, what do you get? You get negative a sine of x. Differentiating minus b sine x, what do you get? You get minus b cos x. Let's call this equation 3. All right, now take a look at this very well. From equation 3 is looking like equation 1. So no, I mean the right hand side of equation 3 is looking like equation 1. So how do we manipulate this? Okay, now if we check, we can factor the negative sign from here. So the 2y dx squared can be written as take the negative outside to give you a sine x plus b cos x. But wait a minute, this is the same thing as y. A sine x plus b cos x is equals to y according to equation 1. So we can substitute this to be y. All right, let's do that. So the 2y dx squared is equals to minus y. All right, so you can see we have eliminated all the arbitrary constants, and we are able to maintain the second derivative, which is exactly what we need. Because anytime you try to eliminate the arbitrary constants, depending on how many they are, you try to retain the highest differential coefficient in that equation. So we have the 2y, the x equals to minus y. So this will be the 2y, the x squared plus y is equal to 0. And this is the differential equation formed when you eliminate the arbitrary constant from this equation. And you can see it is of order 2. Why? Because we have 2 arbitrary constants. We eliminated 2 arbitrary constants. And this is why it is of order 2. Let's take a look at the last example. We are going to look at the last example in this video, which is y is equal to u times e to the 3x plus b times e to the x. So by now, I'm very sure all of you must be guessing that, of course, we only have 2 arbitrary constants in this equation, which means we are going to obtain an ODE of order 2 when we eliminate them. So let us see how we can eliminate this. This is going to be very tricky because e to the 3x or exponential functions in general, there are functions that do not eliminate. No matter how much you take derivative, no matter how many derivatives you take, they just don't go away. So let us see how we are going to solve this problem. So y is equal to u e to the 3x plus b e to the x. Let's call this equation 1. Now we need to take the derivative, but how many times we have to differentiate y because we have 2 arbitrary constants. So the y, the x will be equal to, if we differentiate this, we get 3u e to the 3x plus, if we differentiate this, we get just b e to the x. Let's call this equation 2. Let's differentiate again so that the 2y, the x squared, will be equal to 9 because the derivative of e to the 3x is 3 times e to the 3x multiplied by this. We're going to get 9 u e to the 3x plus b e to the x. Let's call this equation 3. Now, how do we solve this? Because we can see after taking the derivative twice, we can see that we haven't found a simplified version of it yet. So the best we can do in this situation is to solve them simultaneously. That is, you can pick 2 of your choice, any 2 of your choice, and solve them simultaneously and substitute your answers in the others. So I'm going to pick 1 and 2. I'm going to pick these 2. So from 1, if I multiply equation 1 by 3, it will eliminate this term because I will get 3u to the e to the x, negating this, which will take care of this term. So let us do that. I'll multiply this by 3. So I'll multiply this by 3. I'll multiply this by 1. Alright? I'm solving them simultaneously. So doing that, I'm going to get 3y is equal to 3u e to the 3x plus 3b e to the x. Let's call this, we'll call this equation 4. Now let's write the second one. So multiplying this by 1 will not change the value. So the y, the x is equal to 3 u e to the 3x plus b e to the x. Let's call this equation 5. Now if I minus equation 4 from equation 5, I'm going to get the left hand side minus the y dx will give you what? This will be 3y minus the y dx, which is equal to, this minus this will give you 0. This minus this will give you 3b e to the x minus b e to the x. Now 3b e to the x minus b e to the x will give you 2b e to the x. So I'll just clean it and put 2b e to the x. All right, and then I can also clean this. So let me clean this and write it. It's equal to 2b e to the x. Let's call this equation 6. All right, now I'm going to take I want to find the value of v. So how do we find the value of v? I'm going to divide both sides by 2e to the x. Divide this side by 2e to the x. In doing that, I get that v is equal to, this will cancel this and this. So v will give me 3y divided by 2e to the x minus let's put 1 all over 2e to the x times the y dx. So this is the value of v. Now I will take the value of v and I'll put it back into equation 1 so that I can find the value of u. All right, let's do that. So y is equal to u e to the 3x plus v. Now v is the whole of this. Okay, so we are going to put the value of v into here. So this is e, v times e to the x. So we are going to put e to the x outside like this, and then we put the value of v into the bracket. This is 3y times 2e to the x minus 1 all over 2e to the x dy dx. All right, so let us open the bracket. So y is equal to u e to the 3x plus e to the x. Because e to the x multiplied by this, you only get 3y divided by what? 3y divided by 2. You're going to get minus 1 all over 2, because e to the x times minus 1 over 2 e to the x, you're going to get 2 dy dx. So the next step? The next step is to isolate u. So u in this case is equal to, take everything to one side, you're going to get y. This go to the other side, becomes 3 all over 2 times y, right? This comes to the other side, becomes positive 1 over 2 dy dx. All right, all divided into the 3x, e to the 3x. So let us tidy this, let us simplify this. So we can say u is equal to, now this is 1, this is 1y minus 3 over 2y. What do you get? You're going to get minus 1 all over 2. All right, now let us combine it with the denominator, giving us e to the 3x times y, right? Plus what is left here, we're going to get 1 all over 2. Let's combine it with this denominator. This will be e to the 3x times what? Dy dx. So let us rearrange it. I like let dy dx come first, so that u is equal to 1 all over 2e to the 3x dy dx minus 1 all over 2e to the 3x times y. All right, so this is the value of u. Now I'm going to put the value of u and v into equation 3. We've been able to successfully obtain the value of v and the value of u. So we are going to take the values of u and v and put it back into our equation 3. Remember, we didn't use this equation from that equation 1, 2, and 3. We didn't use it, so we have to plug everything back, because it is the one equation containing our highest differential coefficient. So you must always make sure that the highest differential coefficient appears in your final differential equation, which will even give us the order of the differential equation. So let us put the values of u and v back into this equation. So the 2y dx squared will be equal to 9. You can take 9e to the 3x out, plug u into it. So this is u, which is 1 all over 2e to the 3x dy dx minus 1 all over 2e to the 3x y, right? Plus e to the x. Now this is e to the x into v, but this is our v. So that will be this into 3y divided by 2e to the x minus 1 all over 2e to the x times dy dx. All right, let us simplify this equation. So the left hand side, the 2y dx squared will be equal to, now this is 9, e to the x will cancel e to the x, e to the x will cancel e to the x, so we are going to get 9 all over 2 times dy dx, 9 over 2 times dy dx. Now 9e to the x times this, we are going to be getting minus 9 all over 2, because e to the 3x will cancel e to the 3x, leaving us with y. All right, e to the x multiplied by 3y divided by 2e to the x. Now this e to the x will get rid of this one when we open the bracket, leaving us with positive 3y divided by 2. E to the x will cancel it. Then we have minus e to the x times negative 1 over 2 e to the x. It will cancel out. So you are left with minus 1 all over 2 dy dx. Okay, so we are left with this, and the next step is to collect like terms and simplify it. So this is the 2y dx squared is equal to, this is 9 all over 2 dy dx. To bring this with dy dx, bring them together. So this is 9 all over 2 dy dx minus 1 all over 2 dy dx minus 9 all over 2y plus 3 all over 2y. All right, let's add this and this together. If we add this together, this is the 2y, the x squared is equal to 9 half minus 1 half. That will give you 8 divided by 2, the y, the x, minus 9 over 2 plus 3 over 2. That is minus 6 over the 2y, the x squared is equal to 8 divided by 2 is 4. 4, the y, the x, minus 6 divided by 2 is minus 3y. All right, this is the solution to this differential equation, but let us simplify it. So simplifying this equation, we are going to get that the 2y, the x squared, minus 4, the y, the x, plus 3y, and this is equal to 0. So this is a second order differential equation because we eliminated two arbitrary constants, and this is what you get. So in the upcoming videos, we are going to start doing first order differential equations, or we are going to look at methods of solving differential equations of first order.